Good afternoon, everyone. I'm glad to present our work, Chitu, Avoiding Unnecessary Fallback in Byzantine Consensus, and I'm Rongji. This is a joint work with Xiangzhe, Xiaofeng, Lei, Guangtao, and Shengyun. Most partially synchronous protocols like PBFT and Nintendo Mint are leader-based and usually separated into two components. The normal case is that a single leader coordinates other nodes to replicate its proposal, and the view change that the new view starts with the new leader elected if the previous leader is problematic. During view change, partially synchronous protocols rely on a predefined maximum network delay, the big delta, to help trigger the leader replacement, and no available service can be provided. Even worse, if network synchrony assumption does not hold, partially synchronous protocols may be involved in consecutive view changes, forfeiting the Leibniz property. Asynchronous protocols, in contrast, have no synchrony assumption and do not pre-select the leader. Asynchronous protocols require every node to make a proposal in each round and participate in several phases of message exchange. A coin flipping phase is used to help non-faulty nodes converge and reach a final agreement, but incurs more rounds of communications and increases latency for committing blocks. For recently proposed DAG-based protocols, they use coin to select a validated block and commit previous blocks according to the ages in DAG. According to the above, we observe that leader election, timer, and random coin are all located on the critical execution path, dragging down the system performance. We reconsider the consensus problem from its first principles. Neither any special role or the maximum network delay, the big delta, nor randomization is intrinsic to the consensus problem. Thus, inspired by two fast-path-based protocols, my Tumblr and Red Belly, we focus on the framework applying the fast path, where correct nodes can try to reach agreement merely based on message exchange to skip costly timeout events or random coin, but only resort to a fallback mechanism if the fast path fails. First, we simplify the discussion by focusing on one-shot consensus. Any solution to the multi-valued consensus problem requires each proposer I to make a proposal Bi. After several phases of message exchange, correct nodes eventually decide on a single proposal or a subset of all proposals. Eventually, each proposal is either committed, output 1, or aborted, output 0. Then, to better illustrate the fast path of our framework, we introduce a simple concrete example. Example 1 shows how the fast path works. Each node I makes a proposal Bi and propagates Bi to others. As at most F nodes may be faulty, after receiving n-f proposals, node I casts a vote on each proposal by notifying others of all the proposals received. Finally, after receiving n-f such notifications, node I selects the proposals that have each obtained at least f+1 votes as the candidates for final decisions. Here, we categorize each proposal into three cases: one valent, zero valent, and a bivalent. We call the first two univalent. If a node observes that every proposal in one round is univalent, it can commit the one-valent proposals and abort the zero-valent proposals through the fast path. In this example, node 0 can immediately commit B0, B1, and B2 upon observing they are one-valent and B3 is zero-valent, while other nodes will only select B0, B1, and B2 but not B3 and the candidates for further negotiations. Then we give example 2, where the fast path fails because some proposal is bivalent. We can see that B1, B2, and B3 are one-valent, but B0 is bivalent, making nodes have discrepancy in their candidate choosing. Node 0 and node 1 see B0 as a candidate, but the other two nodes see B0 as aborted. And that is why a fallback mechanism is needed. Then, we formally introduce a fair fallback framework. If every proposal in one round can become univalent based on message exchange, then nodes can directly commit them through the fast path without the leader coordinating. And the fallback mechanism is needed only if some proposals are bivalent, so as to guarantee all proposals are committed in the same final order. Our framework can apply to protocols under different assumptions. For asynchrony assumptions, if the adversary controls message scheduling of all nodes, some proposal may forever be bivalent. To defend against such a powerful adversary, our framework can introduce random coins as a fallback mechanism, and we obtain Chitu protocol. Maybe more interestingly, if we assume the adversary can control message scheduling, but cannot always break synchrony assumptions, we can instead integrate the delta timer into the fast path and obtain a partially synchronous protocol, like applying the fast path to Bouchard. We may even remove timeouts but keep pre-selected leaders and obtain an asynchronous protocol under fair schedulers. We further generalize the design of the fast path. There can be different ways to instantiate the fast path. Recalling the examples before, we derived the following conditions. Con C is the conditions for the fast path to commit one-valent proposals, like B0, B1, and B2 in example 1. Con A is the conditions for the fast path to abort zero-valent proposals, like B3 in example 1, and Con F is the conditions for the fallback to commit a proposal, like the bivalent B0 in example 2. For any proposal, these two invariants must hold so as to guarantee that the fast path and the fallback commit the same proposals. Guided by this design, now we are facing two challenges in details. First, how to ensure safety properties under Byzantine faults. We use Byzantine Reliable Broadcast (BRB) to make correct nodes deliver the same message. Second, how to efficiently integrate two paths with no switch and guarantee each path commits the same set of proposals. We give a full-fledged solution, Chitu protocol, integrating the fast path and the fallback both into the DAG structure. Now let's dive into some details. First, inspired by task and DAG rider, every node in Chitu proposes a vertex round by round to dynamically construct the DAG by BRB, and thus all correct nodes eventually observe the same DAG. Compared to task, the main difference locates in the commit rules. Due to the fast path, Chitu decides and commits vertices also in a round-by-round manner. The fast path uses vertices of round R plus 1 to help decide round R leaderlessly, while the normal path uses a selected leader to help decide preceding rounds. Moreover, the adaptive wait mechanism is designed to further reduce latency by increasing the chance of the fast path univalent commits. In DAG, a vertex in round R is not only a proposal of round R, but also a notification of the proposals it observes. Thus, Chitu can naturally embed the message pattern of the examples before into the DAG, and we can follow the definitions of the valent for proposals. Case 1 illustrates how the fast path works when all vertices in round 1 is one valent. All vertices of round 1 can be committed through the fast path after round 2, without the leader in the later round, where only two DAG rounds, that is 4 communication phases, are taken. Even if the vertices of round 1 are committed in the normal path, the leader of round 3 connects to each of them via at least f plus 1 vertices of round 2. That is the same as the candidate defined in the examples before. We say they are strongly observed and will be committed by the leader. Case 2 illustrates when V2, V3, and V4 are 1 valent, but V1 is 0 valent. The leader also strongly observed V2, V3, and V4, but not V1, because it is observed by only one vertex, V5 in round 2. When the fast path fails, Chitu falls back to the normal path. Chitu selects leaders by random coins, like tasks. Leader vertices can recursively decide preceding rounds. The diagram below illustrates how Chitu commits vertices through the fast path and the normal path together. The number in each circle denotes a round after which the corresponding vertex is committed. Round 1 and round 2 are decided through the fast path, and thus their strongly observed vertices are committed immediately. In round 1, the vertex proposed by node 3 is committed indirectly by round 2, as it is observed by the strongly observed vertices of round 2. Round 3 is decided through random coins, for the vertex proposed by node 2 is bivalent. Even if round 4 is decided through the fast path, it cannot be committed until the leader vertex V1 of round 5 is selected, which decides round 3. In round 3, the vertex proposed by node 2 can also be committed because it is observed by a strongly observed vertex proposed by node 0 in round 4. By such commit rules, it can be ensured that every round is decided either by the fast path or by the same leader vertex. In the existing way of DAG construction, every node advances to the next round as long as it delivers n-f vertices of the current round. Due to the discrepancy in round-trip time between nodes, some vertices may be connected by more than n-f edges, while others are connected less and stay bivalent. The first diagram illustrates this scenario, and the fast path fails because V4 is bivalent. To mitigate this problem, we wonder, what if the node waits for more vertices delivered to advance to the next round? Intuitively, more edges are connected to help V4 become 1 valent, as shown in the second diagram. However, it is irrational to simply introduce a timeout mechanism for waiting, which will be an inevitable barricade on the fast path. We observe that any vertex received by f plus 1 nodes can be propagated to every correct node eventually, and definitely can be delivered through BRB. Thus, we design the adaptive wait mechanism. When node delivered n-f vertices, it has to wait for the vertices already with at least f plus 1 votes to be delivered, and then it can advance to the next round. By doing so, the bivalent vertices have more chance to become univalent, making the fast path more likely to be gone through. We have implemented Chitu in Golang and conducted evaluations against open source implementations of Task and Bootstrap. The testbed is Amazon EC2 platform. For these tests, the nodes were deployed on T3.2 XLarge virtual machines, each with one client on the same machine. The payload size for request was set at 1000 bytes, which represents the trend towards larger transactions for blockchain application. We first measured the for-free performance. We gradually increase the client request sending rate until the system is saturated. The end-to-end latency of Chitu is around 500 milliseconds when the system is not saturated. In 4-node tests, Chitu achieves up to 82.5% reduction in latency compared to Task. This is mainly because most vertices in Chitu are committed through the fast path at small scales. In the best case, only 4 communication phases are taken and the random coins are bypassed. Even in 100-node tests, the latency of Chitu is still much lower, with around 50% of vertices completed through the fast pass. Moreover, in the normal pass, the probability to select a valid leader is higher in Chitu, because more edges are connected between rounds thanks to the adaptive weight. With lower latency, Chitu can also bear heavier workload and achieve higher throughput. We then measure the performance under crash faults. We disable F nodes in advance. Chitu has lower latency and higher peak throughput also in this scenario. This is because when F nodes crash, each vertex can observe only n-f vertices of the last round. This implies that each vertex are observed by exactly n-f vertices of the next round, and no vertex is bivalent, and thus Chitu can completely skip random coins and achieve fast termination. We also theoretically analyze the performance of Chitu compared to task by Tumblr and Rebelli. More results, such as the performance improvement by adaptive weight, the pseudocode, and the correctness proof, are provided in our paper. In conclusion, we introduce a fair fallback framework for reducing latency in BFT protocols in a leaderless manner. Our framework opens avenues for future work. Other partially synchronous or asynchronous protocols, or protocols under crash fault model, even protocols under fair schedulers, can also adopt a similar idea to achieve fast termination. And we introduced Chitu, a DAG-based asynchronous protocol following this framework. Chitu not only retains the simplicity feature of DAG protocols, but can also bypass expensive random coins and achieve consensus efficiently when most nodes are in consistency about their observations. That's all. Thanks for your attention. I'm happy to answer any questions.